Okay, so thanks for giving me the opportunity to present my works here. So today I want to talk about the Chairings and augmented Chairings of uniform matroids and Q-uniform matroids. So let's first recall that the matroid N, it can be characterized by a lattice of flats Lm. So this is a finite geometric lattice. And in particular, we care about the uniform matroid UN R. R is the rank of the matroid, and the ground set is 1, 2, 3 to N. And the lattice of that associated to them is something called the truncated Boolean lattice. So these lattice consists of subsets of 1 through N sets of cardinality from 0, 1 up to R minus 1, and then jump to N. So for example, when N equal to 4 and R is 4, the lattice of that is just the whole Boolean lattice. You can see it's all the subset of 1, 2, 3, 4. And when R is 3, we need to, so rank is 3, we need to truncate all the subsets of cardinality 3. So we get this is lattice of flat. And when R is 2, we need to further truncate the cardinality 2 subsets. And when R is 1, these are the lattice of flat. So basically, when we think of uniform matroid, we just need to think of the lattice of flat associated to them, and the lattice of flat are these kind of truncated Boolean lattice. Okay, so sorry. Okay, so now the Q analog of the uniform matroids are we call the Q uniform matroids denoted as UNR of Q, and similarly the lattice of flats associated to them. This is instead of the lattice consists of subset of 1 through N set. Now this should be the FQ subspaces of the finite field FQ to the N. And those subspaces have dimension from 0, 1 to up to R minus 1 and then N. So when N is 4 and R is 3, rank 3, the U43Q, its lattice of flats are just subspaces lattice of FQ to the 4 with dimension from 0, 1, and then 2, and then jump to 4. So we truncate the dimension 3 part. And here, these are just the number of the subspaces appears in each of the layers. So you can see the number here. These are the Q binomial coefficients defined as the following, using the Q integers and then the Q factorial. And when Q approaches to 1, like Q approaches to 1, this just go back to the normal uniform matroid, and this lattice of flat is just the normal truncated Boolean lattice. So now, given loopless matroid M on 1 through N set with lattice of flat Lm, the Charing of N is, we denote it as A of M. It's defined as the following. So it's a quotient of the polynomial ring with integer coefficients whose variables are indexed by the lattice of flat, remove these empty sets. And if you look at the numerator here, this looks complicated, but actually this is the Stanley-Reisner ring of the order complex of the Lm, remove the empty set, and then you need to model some general linear form. So these are, maybe I can make, sorry. Maybe I can, so these are first introduced by Fechner and Zvinsky in 2004 for any atomic lattice with respect to some subset called the building sets. And then Adiprosito, He, and Katz in 2015, they apply it in the case of lattice of flats of a matroid. And so they just call these things the Charing of the matroid, which is the definition we saw here. Yeah. And but so what we care about is actually Fechner Zvinsky in 2004. They not only defined the ring, but they also found that this Charing is Z-free, and using Grobner basis, they found a monomial Z basis. of these Charing, which has the expression like this. So you can see these monomial bases are indexed by chain. So these are lattice of flat. They are indexed by a chain of a flats in your lattice of flats, and with some restriction on each of these exponent A1 to AL. So for example, when your M is the uniform matrix U43, these are the corresponding basis elements. And if you compute, you count the cardinality in each degree, these will give you the Hilbert series of the Charing of uniform matrix U43, which is this thing. Yeah. So Hamster and Rao-Simpson in 2021, so they compute the Hilbert series of a Charing of Q uniform matrix, and they found it has the following combinatorial expression. So it's related to counting major and minus exceedance, major index and minus exceedance and exceedance over permutations. And then you need to, so when your uniform matrix, Q uniform matrix have rank R, you need to subtract some term related to this rank R. And the term you subtract here also related to the number of fixed point of your permutations. And in particular, for the special case when rank is n-1, this Charing of Q uniform matrix n-1, turns out these terms can be simplified into these. And now like we only counted over the derangements in Sn. So these are just the permutation without fixed points. And we will need this polynomial later, so I'll denote. So if you don't have a -1 here, we will denote these polynomials dn of qt, which will show up later. And when R is n, it turns out we just don't have these things subtracted here. So these will just be counting all the permutations over all the permutations with q to the major minus exceedance and t to the exceedance. And these are the Qolarium polynomials and qt studied by Qolarium and Wax in 2007. So Brandon, He, Mason, Proudfoot, and Wang in 2020, they consider an extension of the Charing, which is called the Augmented Showering of a matrix. And this is defined as the following. We denote it as A tilde M. And you can see, besides the variables that coming from the lattice of flat is xf, we have extra variables, this is yi. So these actually, augmented showering contains information both from the lattice of flat of your matrix and also from the independence complex of your matrix. But so it looks complicated, the definition, but we just need to know that. So in my previous work, and also independently by Chris Ure, Jung He, and Matt Larson in 2022, we showed that this augmented showering has the following expression of its z basis. So it's similar to the Charing case, just the monomial, its first term has a different condition, this A1. And when your M is uniform matrix, these are the basis elements we have. And if you compute the cardinality in each degree, this is 1, 11, 11, 1. So this will give you the Hilbert series. You can get the Hilbert series of augmented showering of uniform matrix, which is this thing is actually the Qolarium polynomial when n equal to 4. And so our motivation is to give augmented showering result that parallel to what Hamster, Rao, and Simpson's Charing's result. And to introduce that, we need to introduce another extension of permutations called the decorated permutations. So a decorated permutations on 1 through n set, you can think of it as a permutations on a subset of these set, 1 through n set. For example, when n is 5, these 2, 1, 5, well, this is permutation on the subset 1 to 5. And you as a map, using two-line notation, you can see it's 1 map to 2, 2 map to 1, and 5 map to 5. And there's no 3 and 4, so 3, we just write 0. 0 here, and then we record these 1, 2, 1, 0, 5 here. This is the one we call this the one-line notation of our decorated permutations, and this theta is just denotes the permutations on the empty set. So when the one-line notations are all 0, and we denote the Sn tilde to be the set of all decorated permutations on 1 through n set. So when n equal to 2, these are the possible decorated permutations. This is the one-line notation, and use the one-line notations, we can extend the number of exceedance and major index from permutations to decorated permutations. The definition is similar, but now just be careful that the exceedance of theta, we define it to be -1, and major of theta is also -1. And also that we can define a number of fixed point of second kind, denoted as these things. These are just counting the number of zeros in our one-line notations. So if we compute the major minus exceedance and exceedance over these decorated permutations, you will get these things. So, and these are actually something called the n tilde qt is a Q binomial Qolarium polynomial studied by Hsin-Chieh and Wax in 2020. And so these are examples. You can, if you compute using the statistic, you get this thing, and use the definition here, A2 tilde t, you will get the same thing. Yeah. So our main result is, so we compute the augmented showering of Q uniform matroids, and it turns out that we have two different kind of formulas. One is these kind of closed formula type, and you will see it will be like this. And the other is similar to Hamilton, Rao, and Simpson's result, is a combinatorial expression, but instead of permutations, now we're over all decorated permutations. And also we need to subtract these R related to the rank. And then the fixed point here becomes the fixed point of the second kind. And when R is a -1, it turns out that the Hilbert series becomes just counting all the permutations. So this is the Qolarium polynomial. And when R is n, there is nothing being subtracted. So this is just counting all the decorated permutations. So this is binomial Qolarium polynomial, Q polynomial. And you can see that in, if you recall that the Hamilton, Rao, and Simpson's result, they only have one expression, this combinatorial expression. So we also found that for the Charing case, we have a similar closed formula expression like these. But instead of the augmented Charing case, this is the Qolarium polynomial, but here this is the DJ of QT. This is counting the derangements. Yeah. And so so these two expressions when Q equal to 1, this is also independently found by Ferrani, Mathan, Stephen, and Backy in 2022. Okay. So sure. So now we so far we look at these Q analog related to derangements, permutations, and decorated permutations. So Hsin-Chieh and Wax, in their work, they also consider a symmetric function analog of these Q analog. I didn't define them, but these Qn0, Qn tilde, these are symmetric function polynomial. And when you replace variables x1, x2, x3, so on by 1q squared, and multiply by something, you will get back to these Q analog polynomial. Hsin-Chieh and Wax, they also have a F expansion for this QNXT, which has this form. So this F is the Gassot's fundamental quasi-symmetric function, and DEX is just some set statistic kind of variant of descent set. Yeah. And so our result is that we show that this DEX statistic can also be extended to decorated permutations. And furthermore, these Qn tilde also have a similar fundamental quasi-symmetric function expansion using these DEX. And now if we consider just the Charing, if we consider just the basis we found for Charing of uniform matroids and augmented Charing, actually, so I didn't write it down here, but you'll see actually they are Sn invariant. So both of these Charing and augmented Charing, they carries an Sn representation. And we also compute the symmetry function corresponding to these representation. So they are graded for being a series. And it turns out that it will give us, each of them also give us two different expressions like these. So the Charing case, you have these closed formula version, and also have these thing. The second one is kind of like combinatorial expression, similar to the Q analog version, and similar for the augmented Charing cases. Yeah. And you can kind of see these two things. These are symmetric function, if you change variables x1, x2 using 1q squared and so far, and you will get back to the Q analog we saw in the Q uniform matroid cases. So we actually have these two different kind of way to get Q analog. One is by looking at the Q uniform matroid, but one is like you looking at the uniform matroid. We consider the Sn representation on these things and doing this principal specialization, you get a Q analog. And it turns out they give you the same thing. Yeah, so it's kind of interesting. You have a different way, but you get same stuff. And okay, I think I run out of time, so that's all I want to say.